So continuing on with part 6, which is Newton's second law of motion. Part 2, we're going to now start considering some additional information now that we have a better understanding of what weight is and how it relates to mass. So on blue page 27, we have, this is actually 3 pages of a worksheet called Dropping Masses and Accelerating Cart. So we're going to work through these each one by one and go through them. So the first one is already done for you on your worksheet, and it says, consider a 1 kilogram cart being pulled by a 10 Newton applied force. According to Newton's second law, the acceleration of the cart is A equals F over M. And they labeled their picture with 10 Newtons and 1 kilogram for this cart. So when 10 Newtons divided by 1 kilogram, you end up with 10 meters per second squared. So for number 2, it has consider the acceleration of the cart when the applied force is due to a 10 Newton iron weight attached to the string draped over a pulley. Will the cart accelerate as before at 10 meters per second squared? So we need to figure out the information. So at this point, the force is 10 Newtons, and this must be because there's a 1 kilogram weight here, because we already know that weight equals mass times g. So from that, we can figure out the mass here is 1 kilogram. There's also 1 kilogram here at the cart. So that means we have a total of 2 kilograms in this scenario, and there is a force of 10 newtons. So for A equals F over M, we've got 10 newtons, and there is 2 kilograms. That will give us an acceleration of 5 meters per second squared. So that is different than our previous answer where we had 10 meters per second squared. That's because we have more mass here. Number 3 is similar in this fact now that they ask us to find the acceleration of the 1 kilogram cart when 2 identical 10 Newton weights are attached to the string. So now this time we have 1 kilogram and 1 kilogram hanging off the string, 1 kilogram in the cart, so that would be a total of 3. And the total force here is that there are 2 individual kilograms, and that means we end up with 10 newtons for each of these, and the force will now be 20 newtons because there are 2 times 10. So our total force is 20 newtons, our total mass is 3 kilograms, and now we have an acceleration. If you plug that into your calculator, 6.7 meters per second squared. And you probably do want to be double checking the math here because I have been known to make mistakes. So if I do, please let me know. Number 4 is going to be the same thing, only now we're going to add another weight off. So can you figure out number 4 and what it would be by adding another single kilogram weight here? So we're going to increase our mass, we're going to increase our force, and now we're going to end up with 30 newtons as our force and 4 kilograms as our mass. So we end up with 7.5 meters per second squared. Number 5 has find it when you have 4 weights dangling off, but they don't have a picture. So now you're going to add 1 more kilogram, and you're going to add another 10 Newton force. And for this one, you're going to end up with 40 newtons for your force, 5 kilograms for your mass. So your acceleration is going to be 8 meters per second squared. Number 6, this time 1 kilogram of iron is added to the cart and only 1 iron piece dangles from the pulley. So now we're changing our picture again. This time they've got 1 kilogram in the cart, 1 kilogram for the cart. So there's now 2 kilograms here, as well as 1 kilogram hanging off the side. So we have a total of 3 kilograms, and our force is going to be 10 newtons because there is only 1 10 Newton weight. So we've got 10 newtons divided by 3 kilograms, and that equals 3.3 meters per second squared. Number 7, now we're adding another kilogram into our cart. So now we have 1, 2, 3 up here with the cart and a 4th one here, so that would be 4 kilograms total. We still only have 10 newtons of force hanging off here on the end, so we've got 10 newtons divided by 4 kilograms, which gives us 2.5 meters per second squared. Number 8, they're going to add another kilogram to the cart. Can you figure that one out? So what I got was there's a total of 5 kilograms for the mass. So there's 3 in the cart, 1 for the cart, and the 1 hanging off here. So that's 5, and we still have 10 newtons. So 10 newtons divided by 5 kilograms is 2 meters per second squared. And the last one, they've filled up the cart like this time, but now they have 4 masses hanging off. So we end up with a new force of 40, 4 times 10 newtons, as well as 8 kilograms. So that gives us an acceleration of 5 meters per second squared. So number 10 says to draw your own combination of masses and find the acceleration. You can draw whatever you want here, and I'm going to ask you to do that as part of your follow-up work. Just make certain that I can read it. I really want to be able to see what you drew. Try not to copy one that we've already done. That does defeat the purpose a little bit. So pause the video for a moment and go ahead and do that. Now I want to skip backwards to some pages that we did earlier in this packet. However, we didn't do the complete backside of the page because we weren't quite ready to do that back when we first covered this page. So we're going to go back to page 9, which we left blank. And it has a number of scenarios here, and we're going to try to finish these up and wrap up this page in this packet. So I am separating them out one at a time. So the first one, we have a 600 Newton force hanging down from on this free body diagram. And we should be able to recognize that using our free body diagram, we know that the weight is equal to the mass times g, and if we use g as 10 meters per second squared, we end up, we can rearrange it and find that the mass is equal to the force of gravity divided by 10. So whenever we have this, we can find the mass that would go down in here in this line by taking this number and dividing by 10. We can do that for every scenario. The other thing that we know is that we can determine our net force by just looking at the picture. So our net force here is going to be 600 newtons down. Here, if we look at it, we've got 400 up and 600 down. We know that it's 200 newtons down. So once we have those two pieces of information, the net force and the mass, we can solve for the acceleration by taking A equals the net force divided by m. And the direction of the acceleration is always going to be the same as the direction of the net force. So this is going to be very much like what we did previously on the last page, but now we're kind of adding a step to it to add to the fact that we know a little bit more now than we did back previously. So these are the general steps that we're going to do for all of these problems. So let's take a look. So for the first one, we've got 600 newtons down on this free body diagram. So we know that if we look at the net force, we are still going to have 600 newtons down because it's the only force acting on it. And the mass is going to be 600 divided by 10, which is giving us 60. And to solve for acceleration, A equals F net divided by m. So we take 600 divided by 60, and we get 10 meters per second squared. And the direction is going to be down because that's the same direction as the net force. If we go on to B, we're going to do the same thing. The net force is 200 newtons down. We do that by comparing those two. The mass is going to be 60 because it's 600 divided by 10. And when we take acceleration equals net force divided by mass, we take 200 divided by 60, we get 3.33 meters per second squared. Pause the video as you need more time. C, we're going to do the exact same thing. Our net force, we're going to take a look at this, and we're going to see that they're balanced up and down, but to the left, we have a net force of 2,000 newtons. And we can figure out our mass by taking the gravity and dividing it by 10, and that will give us 800 kilograms. The acceleration is going to be the net force divided by the mass, which gives us 2.5 meters per second squared, and it is also going to the left because that's where the direction our net force is. D, by observation, we can look at the up and down. They're equal, so the net force is the same as this force of friction of 4,000 newtons to the left. Our mass is 8,000 divided by 10, which gives us 800, so that's 800 kilograms. And our acceleration is going to be the net force divided by the mass. Oh, I have the number incorrect here, so I'm going to pause this and fix that. Okay, now it's correct. So 4,000 divided by 800, and it's 5 meters per second squared. And I have the wrong direction. Now it's fixed, 5 meters per second squared to the left. So letter E, we are going to have, by observation, the net force up and down, it's balanced. Right to left is going to be 8 newtons to the right because 22 minus 14 is 8. The force of gravity is 20 newtons, so that dividing that by 10 gives us 2 kilograms. And then our acceleration is the net force divided by the mass, which is 8 divided by 2, which gives us 4. So it'll be 4 meters per second squared to the right. And the last example here, again, observation, up and down, they're balanced. Right and left, they're not balanced. So we've got 44 newtons minus 28 newtons. That gives us 16 newtons to the right. Force of gravity is 40 newtons. And dividing that by 10, we're going to get 4 kilograms. So to find our acceleration, we get 16 newtons divided by 4 kilograms will give us 4 meters per second squared to the right. So once you're done with these and going over them, there's a short assessment for you to take, and they are on this type of simple free body diagrams. And if you have any questions, good luck. Just go ahead and send me an email.